Buddy, Chuck Byers. I work in the Corporate Strategic Innovation Group at Cisco, where I'm responsible for IoT architectures and especially architectures associated with edge and fog computing. I'm going to spend a little bit of time describing what all that means. Before I worked for Cisco, I was a Bell Labs Fellow for Alcatel-Lucent. So we're going to talk a little bit about just in general what IoT means and some of the reasons why we might want to move computation, networking, and storage to the edge, generating these fog computing architectures. We'll talk a little bit more about fog computing. I obviously don't have time in 30 minutes to do the whole topic justice. A little bit about fog computing use cases. I have 3 or 4 of them that I'll talk about. There are hundreds, but highlighting a few might actually help us understand the architectural imperatives associated with fog. There's a standards body that we're involved with and advocating called the OpenFog Consortium. I'll end with a little bit of information about them and potentially how you could get involved if you're interested. All right, just a little bit about where things fit in IoT networks. Cisco often talks about IoE, the Internet of Everything, which is a superset of IoT. So it has the things, the sensors, actuators, user interfaces, endpoint devices of various kinds, but IoE also encompasses people, processes, and data, most typically big data. So the idea is that we've got this full global system that's all of these interrelated aspects are working together to provide some kind of value to customers, subscribers, governments, all the people who would potentially be interested in using IoT networks. I'm going to focus mostly on things for this talk and especially on the performance of networks that are helping those things do their work. There's a thing that we call the DIKW model, which has to do with the distillation of sensor readings as they go up from the endpoint things towards the cloud. So raw sensor readings might come in as raw data, ones and zeros, not particularly useful. Then we go up to the sort of information level where we might take the raw data and turn it into things that might represent trends or might represent information about what's going on at a sort of calibrated sensor level. Then we have this knowledge level, which is trying to figure out how various sensors are interacting with each other and how they relate to a physical system. And finally, there's wisdom. And wisdom is the information distilled to the point where you can use it to make business decisions, where heuristics can be employed, where automated bot-like systems can fully autonomously make decisions about what's going on in your network. You could think about the value of the information as it goes up this chain as being distilled, concentrated, and magnified. So think about it as like grape juice, wine, brandy, and cognac, perhaps. And we're interested in our IoT networks making the finest cognac, the finest wisdom for business intelligence on the top. I'm going to talk a little bit now about a particular variant of IoT that Cisco calls fog computing. We coined that term about 5 years ago, and it's meant to evoke cloud computing, but much closer to the ground. So the same way that that cloud computing has computation, networking, storage, maybe some kinds of accelerators, maybe some kinds of management and control structures inside, we're going to do that same thing, but we're going to push it down physically close to the IoT endpoints. And there's a lot of really good reasons why we want that physical closeness. We're also interested in making them logically close so that we can have more intimate connectivity between the Internet of Things and the actual computation, networking, and storage resources that are making them go. So here's sort of an executive summary on what fog computing is. It's a system-level architecture, and we're extending compute, networking, and storage capabilities down from the cloud through a hierarchy of layers of fog nodes, as we call them, right to the edge. As I said, it's like all the capabilities of cloud, but distributed in a way that's closer to the ground. We think that fog computing, as we've defined it, is a superset of some other edge computing architectures that you might be familiar with. For example, MEC Up to about 2 weeks ago, it was called mobile edge computing. Now it's called multi-access edge computing. They just did a name change. There's also the Industrial Internet Consortium. All these people are worried about what happens when you start putting the computers closer to the things. The work that I'm doing with the OpenFog Consortium is kind of a superset of those worlds. We're doing virtualization, orchestration, a thing called multi-tenancy. We care a lot about scalability. We have a hierarchical approach, and we have lots of security properties that are special to Fog. So all those things taken together, among a bunch of others, are the reasons why fog computing might be very helpful for certain IoT applications. Cisco's got a bunch of market research about what IoT might or might not be. There's a number that shows something like $19 trillion of total economic value over a period of 10 years or so. That would have started in about 2015. So we still got $1.5 trillion or so of that clock to tick. I'm not sure if I believe that number. That's a whole lot of zeros. These things tend to start slower than the pundits expected when they're at the hype cycle early phases. But generally, the area under the curve tends to end up pretty large. So think about, for example, what happened with the World Wide Web. It started a little slow. Now all of a sudden, it's I've got 2 of them on my person web clients. So that's the kind of thing that is that's kind of important. Cisco believes that around 40% of the total IoT traffic supporting that $19 trillion in 10-year ecosystem is going to pass through these edge computing or these fog nodes. Finally, we think that in order for this concept to be successful, the edge computing and fog computing capabilities have to really be open and interoperable, and there has to be an ecosystem, a market that's supporting them with lots of vibrant players. So the real fundamental question that we ask ourselves in fog computing is, where's the optimal place to put the resources, the computation, the network processing, the storage resources? And we might have about 3 choices here. We can try to run everything in the cloud. And in fact, this is the default operation that's done today. You've got a bunch of IoT sensors, and you have a bunch of dumb pipes, and you have a cloud-based application, maybe in Amazon Web Services or something like that, that's trying to make sense of those sensor readings. Unfortunately, you probably can't do that for the full spectrum of interesting IoT applications. In particular, there's a real problem with latency in the cloud. The very best cloud services, the ones that are highly optimized for first-person shooter games, for example, and do nothing else, around 80 milliseconds. A reasonable, more public cloud, more general-purpose cloud, is probably in the 100 to 200 millisecond latency range. That's simply too long for a lot of the applications that I'm talking about, and I'll highlight a few of those in a minute. There's also this need for these things to be potentially mobile. They could be robots or drones or vehicles or trains, and those things are moving around in ways that the cloud sometimes has trouble tracking them and staying connected to them. We also have needs to do geographic focus, which means that we might want to preserve the information associated with a collection of geographically localized sensors in that geography. We might not, for example, care to send information about parking slot availability in Chicago. Might not make a lot of sense to send that to a web server in Iceland somewhere. We care a lot about network bandwidth. Network bandwidth is very expensive. It costs me incrementally $10 per gigabyte. And a 4K video camera can burn a gigabyte pretty quickly. So I might be spending hundreds of dollars a day just to buy extra bandwidth on my AT&T service for that. If I was satellite connected, multiply that by a factor of 10. And then finally, there's these sort of trustworthiness concerns, reliability, security, and privacy. And we must be cautious about what's going on in the Internet of Things, and sending too much stuff, making too much reliance on the cloud, is potentially setting ourselves up for very serious trustworthiness hazards in the network. So some things work fine in the cloud. They'll be the cheapest up there. So if you can run them up there, I'm not advocating that you do something else, run them up in the cloud. But sometimes you can't. If you can't do that, maybe because of a latency concern, another thing that you can try to do is make the endpoints really smart so you don't rely on the cloud for anything. And that'll work in certain applications, and in fact, that's what industrial PLCs are. That's what the environmental monitoring stuff sold by Rockwell and Honeywell for buildings, all that's mostly intelligence localized in the endpoints. The problem is we end up with some serious constraints in the endpoints: energy, capacity, various storage devices, physical space. If it's, for example, man-portable on a warfighter's uniform, it's pretty hard for me to think about having a 16-core processor with a terabyte of storage in that scenario. Environmental's a real problem. If the thing's expected to survive in the Kuwaiti desert as well as in the Arctic, I have a problem with that. Reliability are very serious concerns on devices that really aren't designed for ruggedness. Certainly, modularity is a problem. My iPhone doesn't really have a mechanism for me to change out one camera module and put another in. There's a few phones that may someday let us do that. And then finally, security challenges, especially on the endpoints. They may not have the energy or the physical processor capability to support strong cryptography. And those devices can be stolen. So if I have a traffic camera that's capturing a bunch of stuff, somebody could come up with a socket wrench and take the thing away. So can't run everything in the endpoints, can't run everything in the cloud. Where do we run things? Well, we had these layers of fog nodes in a hierarchy that are partitioned somewhere between the cloud and the endpoint things. Those hierarchical layers are really optimally supporting the different kinds of computation, networking, and storage functionalities. Those hierarchies can have what we call north-south paths where there's different layers of hierarchy. They can also have the east-west paths where different nodes on a given layer of the hierarchy are interacting with each other, perhaps providing load balancing or fault tolerance. In something like a smart city application, you might actually arrange it something like this. So you got the cloud, and then you have layers of access, regional fog nodes maybe running a corner of the city, neighborhood fog nodes maybe running a few dozen city blocks, local fog nodes maybe running one city block or even a large building, and then the ultimate things on the bottom, those might be the cameras and parking sensors and smart trash cans and all the things we've been hearing about today. So the corollary here is, for an important subset of IoT applications, these intermediate layers are essential. There's been a pendulum swing back and forth over the history of computation, and especially network computation, about where we put the intelligence. And you started with mechanical computing that were kind of distributed on people's desktops, and then we had timeshare computers, and then we flipped back to PCs and workstations, and then the internet and the World Wide Web and the search kind of 10 years ago. And now a lot of the intelligence, a lot of the work we're getting done is done on our smartphones. That's perhaps arguably recently transitioned over to where a lot of the intelligence is Siri-like in the cloud. And eventually we think cloud computing and multi-access edge computing is going to represent a swing of that pendulum just a bit back towards the left edge. Got here a list of no less than 18 architectural imperatives for fog computing. Before I hear all grown, I'm not going to talk at length about them. I'm going to talk at length about the first three, then I'm going to say a word or two about the rest of them. We already talked about geographic locality of control. We don't want data to be going past geographical boundaries that might be important. We want mobility to be supported, especially for things like robots and drones and autonomous vehicles. That's very important, and certain things in the fog can help us with that. Reliability and robustness are very important. Some of these services supported by these networks are life-critical, or at least economically mission-critical, and we have to keep them running at all costs. We have a lot of analytics to do here. The act of understanding what's in a frame of video, for example, takes a significant amount of computation power, probably more than I can reasonably afford to put on those cameras. We like the hierarchical organization, as I showed with the regional, neighborhood, street-level nodes. Energy efficiency is really important. If we get to the point where we have, say, 100 billion sensors, maybe supported by 100 million fog nodes, we are going to be needing quite a few more power plants, and we need to do whatever we can to keep the energy on both the endpoint and intermediate computational fog layers as under control as possible. Environmental constraints, a lot of the stuff runs outdoors. Outdoors is typically a harsh environment. We're looking at least automotive class temperature range for some of the work that we've been doing. We need to be programmable at multiple levels. we might want something like an iTunes ecosystem associated with fog algorithms. So we can go to some kind of a portal and say, I want an advanced video analytics algorithm, and here's your choice of 5 different ones. Choose the one that seems to be the most appropriate to your application. Download it with microcurrency or lease it for so many dollars per month. Those would be the economic models there. Multi-tenancy basically means that I might have a fog node that's owned by a service provider, maybe Verizon or somebody like that. Maybe a city owns it, City of Chicago. And then I have lots of different applications that are running on that on sort of a timeshare basis. So it could be that the Federal Express application runs on the City of Chicago's fog nodes. It could be that there's an application for the police department. It could be that there's an application for the Amazon drones that are flying overhead and so forth. All of those are tenants, and in that case, the city would be the landlord. We need to be careful about virtualization and orchestration because this stuff is fairly complex to configure and control, and especially orchestration. We want to make sure that everybody gets their fair share and no more, that everybody's data is protected from everybody else, and so on. Network management must be greatly simplified. If I'm talking billions of things and millions of nodes, I'm really going to have to really minimize the amount of work that the swivel chair people have to do. We need to be scalable. We don't know ahead of time which of our services is going to be the next Pokemon Go. So we need to be scalable in order to crank up the capacity of the network at a moment's notice. Agility in the presence of changing applications and changing threats is important. We think modularity, hardware and software, is important, so we need to be able to plug things in and out of hardware and software backplanes in order to configure the nodes exactly as needed. And then finally, openness. This stuff has to be an open standard because if it's siloed, if it's proprietary, we'll never hit the critical mass that we need for the vision as described. I'm going to go into just a couple of the first 3 of those, I think, in a little bit more detail. So here's some of the possible latency requirements on IoT. This is basically the amount of time it takes from when you make a sensor reading and it goes up through the hierarchy, perhaps to the cloud, and then back down in order to control an actuator. If you can't keep that delay from sensing to actuation under a certain minimum rate, many systems will go unstable. And that's a real problem for critical applications. So some of the applications probably doesn't matter too much. Big data, all the stuff associated with YouTube and home automation, tens of seconds, probably not that big of a deal. When you get into this yellow region where you're doing web searches and trying to read sensors in a way that the physical property that you sensed hasn't changed out from underneath you before the next reading, certainly some things associated with interactivity, smart buildings, that stuff is in the sort of 100 millisecond range. That's about the best you can do on a carefully crafted cloud. So anything beyond that sort of 100 millisecond range on down, those latency requirements are going to require computation that is much more local than the cloud. It costs me, on fiber-connected networks anyway, right around a millisecond per 100 kilometers of distance from an endpoint to the computation resource. So if I'm going from an endpoint sensor here in Chicago up to, for example, a cloud resource in, say, Washington State and back, that might cost me 20 or 30 milliseconds. And obviously, things in the red are going to go unstable under those circumstances. When we get into virtual reality, smart transportation, those kinds of functions, tens of millisecond latency is not uncommon. And when we get into haptics, which is the tactile internet, the force feedback stuff, and various kinds of robotics, like robotic welding, real-time manufacturing functionality, that stuff is really in the 1 millisecond range. So we need a very high performance localized compute resource to manage that. That's what Fog will bring for us. A little bit more now about bandwidth optimization. So we, for example, might have uplinks from these high-performance devices, big cameras, medical devices, jet engines supposedly make about a half a terabyte per flight. We might be looking at tens of gigabytes per day at my incremental cost. That's hundreds of dollars per day of data value there if I'm trying to transport all that raw data up to the cloud for cloud-level processing. If I, on the other hand, have these intermediate fog nodes that can bash that data down by, say, 2 orders of magnitude and only send to the cloud the wisdom, then I'm way under a gigabit per day, and I can reasonably pay $1 a day for that data transport service. So this is one of the reasons why, especially for high bandwidth services, fog computing and localized analytics is really helpful. The third of the attributes I'm going to talk about here is security and privacy. When we were just doing financial transactions and web browsing on the internet, probably not that big of a deal. We probably didn't care all that much about security and privacy. Even when we were doing things like credit cards, certainly a breach is an inconvenience, but nobody's really going to get killed by it. When we start talking about smart highway systems and multi-megawatt locomotives and refineries and industrial robots and drones, which are basically flying razor blades, all of a sudden a hack is a real life-threatening event. And what we don't want to have is great numbers of attack surfaces between these potentially dangerous devices and the cloud. And also some of these devices may not have the right kind of security on them, or they may be compromisable. So what we're going to basically have is a whole selection of security threats between the devices and the cloud. What we can do is put in a layer or multiple layers of fog nodes that are responsible for the localized security processing. Very strong cryptography from those fog nodes up towards the cloud. And probably 90% of the threat surfaces exist between the top of that fog and the cloud. The 10% that's down below is potentially manageable with physical security or perhaps lighter weight cryptography that those individual devices can potentially do. So that's another reason why we might want to do fog. I'm going to go into just a few selected use cases here. I did a fairly rigorous study on where this stuff may apply, and there's a dozen or so vertical markets with particular use cases for each of those markets. I don't think we need to study them in detail. The point is that there's a lot of potential application. Every single one of those things that we wrote up here in black is, we can describe why fog techniques are helpful. So here's an IoT-enabled connected transportation capability. So what we're going to do is put mobile fog nodes on buses, trains, vehicles. We're going to have fixed fog nodes at the stations, and we're going to have fixed fog nodes up and down the infrastructures, the flyways, the railroads, and the highways. And these things working together will let us greatly automate and greatly improve the functionality of these transportation networks. Word about that latency imperative that we talked about previously. Let's say we're doing a collision avoidance application where there's a crossroads of some kind, and we want to make sure that vehicles approaching that crossroads aren't going to smash into each other, smash into pedestrians, or have other safety problems. In the sort of 100 milliseconds delay differential between a reasonable assumption about what cloud can do and a reasonable assumption about what the same algorithm would take on fog, that's about 100 milliseconds extra in the cloud. In that time, highway vehicles or drones might go a couple of meters. High-speed rail, like a maglev, might go a few tens of meters. The Hyperloop might go 100 meters, if you know what the Hyperloop is, going 3,000 kilometers per hour or something like that. Those are the times that I can't be braking if I should be braking, right? So having this local computation is going to greatly improve the capabilities of those collision avoidance, life safety critical applications. Talk a little bit about connected oil and gas. There's upstream associated with exploration and exploitation, midstream associated with shipping and refinery, and downstream associated with retail gas stations and final delivery. I looked up a statistic during that 100 millisecond delay differential between the cloud and the fog. The Alaska oil pipeline will spill 97 gallons of oil. Okay, so if I can make my decision 100 milliseconds faster to close a valve, that's a 97 gallon less oil spill problem that I have to clean up. Cisco has a trial in the city of Barcelona where we are installing fog nodes in order to let the municipal government provide municipal services, as well as services potentially associated with some of these tenants in a multi-tenant model for the people of Barcelona. And we did this trial along with a few of the partners that are listed down below here. And ultimately, we got a lot of really positive feedback from Barcelona to the point where they produced this image right here. So what we're looking at is a map of the city of Barcelona. Every one of those 3,300 red dots is the location of a fog node that would sit in a street side cabinet, a somewhat prettied up version of this thing. They're going to be providing municipal Wi-Fi, public safety capabilities, energy management, street lighting. They're doing a lot of things associated with streets and sanitation. They could be monitoring smart grids. They could be providing a lot of the functions and features that people want out of their smart city. And having them so widely distributed enables us to have the ultimate control over locality, security, latency, reliability. All of the things that we talked about in terms of the attributes of fog are very helpful for these smart city applications. We've got smart city applications percolating in lots of other places, including some talk going on in the city of Chicago right now. So let's go forward and see if we can put in some smart cities, at least in a trial basis, and take a look at what they might bring to the internet using public. And I think fog is going to be essential for at least a subset of the use cases that we'll see. Just a quick word about the OpenFog Consortium, which is a standards body. It's actually more of a standard of a peer-to-peer organization responsible for fog standardization and fog marketing. So there's the founding members. Cisco is, of course, one of them, and some other names hopefully you'll recognize. So we're really just trying to drive the architecture and thought leadership in fog. Here's a full view. Well, this is about a month old, I guess, of all of the companies that are involved with the OpenFog Consortium. And these folks are stepping up to understand how these distributed computation, distributed network, and distributed storage models are going to really help the Internet of Things. A little bit about, I'm going to skip over the detailed goals. I think we saw a lot of that. We have work in technology, we have work in collaboration and innovation, and we have work in education, which is basically what I'm doing up on this podium today, is to try to talk about what this fog model is and what it means to IoT users. This is the 8 pillars of fog computing, and I think I went through most of these already. Let me just talk about a couple that weren't really well defined. Reliability, availability, serviceability. This is the ability of the people in the swivel chairs and the technicians running around in the vans to keep the network running. That's the thing that I wasn't really very clear on. In general, we think that that a network that has these properties with that locality that we're talking about in the fog nodes is the right answer for a very serious set of the IoT use cases. Got to have a big protocol stack in a conference like this, so that's it. That's the OpenFog reference design. These concerns coming up in the gray vertical bars here are things that really are end-to-end concerns. We call them cross-cutting concerns. Then there's a protocol stack of the low-layer sort of hardware firmware here, some service kind of capabilities here, and the higher-order intelligences are up there. We've got a white paper that we published. It's openfog.org. You can find it. We're also going to be publishing a full reference architecture in about 4 to 6 weeks, so stay tuned for that. We've been busy. We've been running just a little less than a month, and we have a little less than a year, and we have lots of accomplishments. The ones that I think we're the most proud of is lots of liaisons being set up, lots of discussion in forum like this, in order to describe what we think the fog vision is and try to get that going. At the conclusions of my talk, we think that fog computing is really going to help improve the performance of IoT networks and really bring value to the customers of those networks. We can have special hardware and software properties in fog nodes, and that'll optimize the capabilities across lots of different applications and lots of different verticals. I only highlighted about 3 of them here, but there's quite a bit of that. Cisco's market research shows that around 40% of the IoT traffic is going to go through these edge computing kind of fog nodes, and most of that traffic will be seriously processed by those nodes, probably doing analytics. we think that these techniques are a key enabler for the ability to get those networks trustworthy, get them ready for mission-critical or life-critical applications. An ad hoc approach or a cloud-only approach isn't going to get you there. And we've got the OpenFog Consortium chartered and running, and we actually are recruiting new members. So if anybody's interested in talking a little bit about how you might want to join us and contribute, or at least listen to the proceedings to stay a little more in touch with this marketplace, I'm very happy to talk to you about that. A couple of URLs for you. That's the Cisco general IoT URL, and there's a sub-page on that about Fog. And this is the OpenFog Consortium's URL. That would be the end of the formal talk. How are we doing for time here? I guess I got time for about 1 or 2 questions.
Yeah, that's about all, I think.
Okay. Thank you.
Thank you.
Up here.
Please state your name.
Thank you.
All right, so Fog is a combination of hardware and software that will go above a local network before we reach the cloud, or it can work without the cloud, just with OpenFog. Because, I mean, Cisco, you guys are everywhere. So at this point, I'm assuming Cisco is controlling the network and everything. It's just that maybe your hardware is not ready to do what you want to do right now. So I think you need to deploy new hardware with the software functionality of selecting all the separate IDs on the network. And if you can go back to slide 5, I would like to mention something. Because I think on top, it's not the cognac. I think on top is your decision next day not to do those 3 things.
Okay.
My name is Radu.
Okay.
So slide number 5,
that one?
the wisdom, the scenario planning, I don't think that's the cognac.
Okay.
I think that's your decision next day not to do those 3 things. It's what best decision you need to take to do your best output on those. That's just my take on
so
this.
that's the hangover I get if I
Yes,
don't
and
do it right.
that's correct. So at
Okay.
the knowledge, you know what's going on. But my question about this slide is, who is taking the decision? Because for you to take a smart decision, you need somebody that analyzes the data. So unless we're talking artificial intelligence, we're going to a different location.
Right.
Thank you.
Today, that decision is being made in a combination of some human in authority with a lot of expert system software supporting their decisions. But ultimately, the planet needs an autonomic nervous system with less than 100 milliseconds response time. And that's, I think, where we'll be heading for a significant portion of these is full automation and robotics. In terms of Cisco's view of hardware and software, we're supporting this as a global industry standard for hardware and software. It turns out that our 819 and 829 routers and IXE 4000 products have extra CPU cores that we know how to turn into Fog nodes. Yes.
If there are any further clarifications, they can be taken offline.
There might be.
There's time for just one more question.
Okay.
And in order not to be unfair to the next presenter.
We'll be fast.
I'll be right to the point. Operations professor, you talked about latency is very important, and then in your diagram you mentioned virtualization, virtualization, virtualization. Why not containers?
Containers are one of the mechanisms for virtualization. We're not being real prescriptive about whether it's containers or KVMs or bare metal or what. We're trying to make all of that part of the possibilities. And for people who are trying to do real tight control of real critical applications, we might recommend containers as opposed to, say, KVM virtualization as a way to get better.
Something like Joyent and Manta, right? That,
I'm not 100% familiar with all the details. I know that a lot of people talk about Docker and Docker-like things as one of the possibilities. What we'd like to really do is extend the wisdom of the cloud down into that philosophy if we can. But there might be a time when we have to break with that wisdom just because we're stuck with security or we're stuck with performance.
I appreciate your concern, and I'd like to join up. And we have some research projects here for autonomous movement framework for drones that we could use your product, like right now.
Okay.
So after the presentation, I'd like to get
Wonderful.
further and
Come and find me. I'll give you all the details.
Thank you.
Thanks, everybody. Appreciate it.
Thank you very much.